Okay, does it work? You see
Yeah,
the slides?
we can see that very well.
Okay. Okay, great. So hello everyone, my name is Matteo Bonanomi, and today I'm here to report or to tell you something more about my experience on using Jupyter notebooks and in general the Python environment in something for which they are really suitable with, which are test beam data analysis, and in particular the high granularity calorimeter test beam analysis for CMS. So I would go with a brief introduction and then just move to a notebook with some examples and demo. So in 2027, CERN is intended to start the high luminosity LHC program. And this brings the luminosity from the current value up to 3 to 5 times, which means that the environment becomes extremely more harsh in terms of both pileup rate, which will go up to 140 to 100 events per bunch crossing, as well as the radiation levels, which go up to 2 megagrays, and so 2 levels, which would make, in particular for our interest of this log, the crystals of the current NCAL calorimeters essentially black, so not usable anymore. All the experiments of the LHC plan to upgrade their detectors, and so they are currently undergoing an upgrade campaign. In particular, CMS is intending, among all the other sub-detectors, to upgrade the current NCAL calorimeters using the high granularity calorimeter. The main tool that you have when you design a new detector to validate the design itself and to study and assess the physics performance are beam tests. And so it's really important to run beam tests in a clean and controlled environment to understand whether your detector will perform as expected. So in 2018, in October, we ran the first very large-scale prototype beam test of HGCAL. With large scale, I mean that a full section of HGCAL was tested, taking data with positrons and pions over a wide energy range and for a total of millions of events. Here you have a very nice event display, and as you see, you have the first part of the detector, which was an electromagnetic component of the calorimeter, and then the second section, which was more complex also in terms of modules, which was the hadronic compartment of the detector. So as I said before, in test beams, you can profit from a very clean environment, so you have more or less everything under control, but on the other side, you still have many challenges to face. In particular, you have, as you see here from the setup of the beam test, you have, of course, many handles to tune, many parts of the data acquisition system and of the detector assembly itself that have to be taken under control. You want to make sure that essentially live, when you take data, you're also taking good data. And so you want to perform some online data quality monitoring. You want to have fast access to data because every time you take data, you don't want to spend time to process these data, move them somewhere like locally on your machine, and then have to rerun them, which is, this is a problem that applies to test beams, but in general to all our tasks in high energy physics. And then you also want to make sure that all the steps of your analysis workflow run as expected. And to do this, in most of the cases, of course, you want to develop some preselection cuts. You want to clean the data from noise or from some unexpected behavior that you observe. Then you want to run data to simulation comparisons. And at the end of the day, you want to get to a paper or to some physics performance assessment, which means to run a statistical analysis. All these tasks are tasks that are really suitable for Python environment itself, but more in general for Jupyter notebooks. And so let me now go to something more in detail on a typical use case of Jupyter, using Jupyter notebooks with okay, still sharing, yes, within a test beam campaign. So as I say, the first part, well, okay, say here, the first part of the test beam campaign will be something very easy. So you don't really need some complicated libraries or anything. You just, in this case, we import uproot, we import pandas and numpy, because the main aim of this task is to make sure that your data are actually behaving as expected, that you are collecting quality data, and so you want to run some live data quality monitoring. And so here we have just the path of our data. We don't need to get the data locally or to our machines, which we access them directly from US, and then we want to run some event displays. This is the first thing that we can do. To do so, we handle our data in this specific case, in this specific example, using uproot. We know that the most probably famous file format is root. There is the root framework, and we have heard in this workshop about PyRoot, which is also a powerful tool to deal with the root files. In this specific case, I'm using uproot and dumping the files into pandas data frames. So the first thing you want to do is just to open your data and to make sure that you can look at the most interesting observables that you have in your data set. And so I just write a wrapper function to read my data set in a form of data frame. So here I will open the file and I will access the branches that I'm interested in. And in this case, I'm interested in the branches that really define the acquisition of our data. So the electronics, mainly the chip, the module, and the channel itself of our detector, and then the two observables that rely on the data acquisition itself, so the high and low gain amplitudes that we can read. And then we can also append some some branches for the simulation, but this is something that may become in a later stage. So after reading our data, we also want to check not only the quality itself, but also some observables like the energy deposit in our calorimeter, the longitudinal profile being the energy deposit in each layer. And so also the same thing, but not for the energy deposit, but for the number of hits in each layer. To do this, and this is something I found very useful, like working in this kind of environment with Python and using uproot, or in general flattening the structure of the usual T-trees of root, you can just avoid looping over all the events that you have in the T3, writing one line to get to your observable, which is quite, which is something very, very useful when you have to perform very fast coding just to check the main observables and the main features of your data. So as a first step, we want to check the quality of our data, looking at the, in general, reconstructed hits. First of all, we want to look at the X, Y, and Z, so the distribution of our event in the calorimeter. But then we also want to look at the, so this would be something which connects to what I said before of data quality monitoring, live data quality monitoring. But then you also want to measure whether your reconstruction and data taking are working fine. And so you want to look at the high and low gains, meaning the amplitudes of the signal that you're collecting. So for example, here I read one of our data sets, and equivalent for Monte Carlo. This specific run is a 20 GeV run. And here you have the dump of the data frame itself. You see that the interesting thing that allows you then to be very powerful when performing all the Python operations with pandas data frames is that the event is flattened. So in a typical root structure, you would have, or also if you were working with Jupyter arrays, you would have an array sort of table, while here we have just columnar data with all the events just flattened for all the properties. So first thing, looking at the quality of our data. To do so, we want to perform something very fast, not very, say, rocket science, but that already can give us some hint of what we are collecting, which is an event display. What is an event display? Just looking at one of the events that we are collecting, we want to look how does it appear in our calorimeter, in our detector. So in this specific case, we just plot the event. Sometimes I'm using just wrapper functions for the plots, but then you have the link to the notebook if you want to go deeper. But this is just plotting stuff. But you see that we can have nice plots of the behavior of our, in this case, electromagnetic shower in the detector. And so we have the three planes in which the shower is developing, along with the three-dimensional view. This plot is not really useful in terms of measuring the physics performance of the detector, but already gives us some hint of how things are behaving. We see that even if we are measuring electrons, we already have some events or some hits in the back parts of the detector, meaning in the hadronic part. the hadronic compartment. You would not expect it, but this is related to noise. And so this is something we do not worry about, but it's interesting to see that it's not completely clean our environment. Then one other interesting thing that we can observe is that we can distinguish maybe two tracks entering the detector. And this is one of the most important things of high granularity calorimeter, the advantage of being capable to distinguish multiple tracks that enter the detector. And this can be an information that maybe later on in the offline analysis we want to exploit for some MVA techniques or clustering techniques. Then the event all in all looks good, but we already see, especially in the XZ plane, that the first layer has something odd in the sense that we observe a larger energy deposit than in the second and the third layer. This is something you would not expect. As the shower enters the detector, it would be a flat shower, and then it would start developing. So we want to start pinning down all the features that can lead to this strange behavior in layer one, for example. And this can be done already in data taking phase. So the first thing you can do is, okay, is to ask yourself, okay, let's see how my data acquisition is going. So how my signals, my electric signals are being collected by my modules. And so I want to look at the amplitude in terms of low and high gain, and to see how they distribute in my high versus low gain plane, because this is the information that at the end of the day you use to reconstruct the energy deposit in your calorimeter, right? So what you do is you would expect a linear relationship between these two observables, so between the low and high gain. But then in this specific case, if you plot the two high versus low gain, you observe that you of course have the expected linear relation. Otherwise the event display already would be completely messy. Then you have a saturation region, and this is perfectly expected because high gain doesn't work linearly through the entire low gain range, but then you have only the linearity range, which is the one that you actually exploit in reconstruction. But then we have something weird going on in this around 400, between actually 300 and 400 ADC counts in low gain. This is something which is in principle not expected. It's not something that is directly related to the events reconstruction, because these properties are directly properties of the data acquisition system. And so it's something that you, of course, want to know where it's coming from and then take care of in the offline analysis. And so our structure of the modules is typically one module as 4 chips. So the first thing we can do is to, well, here we look at overall shape of the high gain versus low gain, is to pin down to different modules and to different chips this information. And if we do so, we see that while chip 1, 2, and 3 actually behave very well, then in chip 0, there is something which is odd. And so the information that we have seen before and that is messing up the event display that we looked at first is actually contained in chip 0. And this is, along with the event display that we saw, something that can already be used to create some sort of mask, because we saw in a qualitative way that layer 1 was behaving strangely, in the sense that we were having a larger energy deposit, and then we see that in chip 0 we have a large charge collected for the low gain in the linearity region. So this is something that if you combine the two information, you would expect chip 0 and layer 1 to be the faulty one, but then you can, and you have to make sure that this is the case, and so you can deepen this sort of information looking at the occupancy plot, where you plot the X versus, so essentially the occupancy plane, so X and Y plane, along with the energy deposit. And as we see, we have the core of the shower, or the electron beam, that is entering in layer 1 and developing through all the layers. Here, plot just the first 4 layers. But the interesting thing is that, as physically expected, the shower is developing, going deeper in the calorimeter, because we see the beam spot becoming larger and increasing in energy. But then we see a region in chip in layer 1 in the first module, which is completely saturated, in the sense that what you would expect a mean energy of around 8 ADC counts, here you have up to 10, 12 ADC counts. So if we look at the distribution of the chips in the module, and again here, we are just performing sort of exploratory analysis. We're just looking at the properties in terms of producing many plots to make sure that everything is going consistently to what we expect in the data taking phase. and we already found a problem. So this is something that we want to take care in the final steps of the offline analysis. We see that this is the distribution of the cells per each chip in each module, and we see that chip 0 is actually the one that in the previous occupancy plot is completely saturated. And so we can say, okay, completing this exploratory analysis on our dataset, we found that chip 0 in layer 1 is faulty, and we can then go down to the setup itself and make sure why this is faulty, or if we don't find a solution because it's actually a broken chip, we have to make sure that this is essentially masked in the final offline analysis. And in fact, if we do so if we apply a masking, this is something similar with respect to what we've just seen with the PhET example, very much simpler. But if we apply a selection to remove this this chip and this layer in X and Y, so in high versus low gain, we see that actually the odd feature is completely gone. Once you have done this, then you are already close to moving to the final analysis, but what you want to do is making sure what happens then in the observables that you are going to study in the final analysis. So we can look at the event display again after having done this masking. We apply some masking related to the noise, which is something that's not covered, but you can arrive to this second masking in the same way. And what we see is that the masking led us to a cleaner situation in the backwards part of the detector, and then also to a substantial improvement in layer 1, which is now the event display has the phase that we would expect. So an electromagnetic shower which enters and develops throughout the depth of the calorimeter. Then we can look at the observables. And so now that we have found the problematics in our data set, we can try to understand how them would affect the final offline analysis. If we do so, what we can look at are the observables that we defined at the beginning, namely the energy sums, so the energy deposit in the calorimeter, or the longitudinal profiles. If we do so, we looked at a comparison between data and Monte Carlo for the energy reconstructed in the calorimeter. Here we just sum all the energy in each module, and we see that the black histogram and the orange histogram are the direct comparison that we would have at the end of our data taking. The orange histogram is what you would expect, so the simulation. The black histogram has a lower distribution and especially a broader distribution. And we already know where this comes from. It comes from the layer 1 and chip 0 that we found to be faulty in our data taking. In fact, when we mask chip 0 and layer 1, we see that the distribution becomes substantially better in agreement with Monte Carlo in terms of shape. Of course, we lose some energy because we are removing some energy from our data taking. This accounts for 8% of energy discrepancy between data and Monte Carlo. And so not only you have to make sure that in the final offline analysis, you take care of masking this faulty chip, but you also have to correct for this, say, artificial energy discrepancy that you have introduced. Same thing for the energy deposit.
So maybe a couple of minutes away from where we would like to start taking the questions. So just encourage you.
Yes, I will just drop.
Thanks.
So same thing for the energy deposit in each layer. Then once you set up everything, you can move to the final and offline analysis, which can also be done using Jupyter notebooks. Like in this case, you can define some user-defined helper functions or libraries that allow you to repeat what you have done and then to perform the analysis. And I will go a bit fast of this. The main point is, now that we know which are the features, and this is done directly in data taking phase, then you can define all the energy and all the runs that you want to study. You load all the data, and then you measure the energy resolution. This is an example. For 80 GeV, the energy resolution is measured running a Gaussian fit of the core region. An iterative Gaussian fit turns you the mean energy and the sigma of this distribution. You do it for all the energies that you have collected and for all the data that you have collected, and you get to the final measure, meaning in this case, the energy resolution. So to conclude, this is an example of the application of Jupyter notebooks and the Python environment itself using in a test bin campaign, so specifically for the high granularity test bin campaign. Jupyter notebooks turned out to be very useful because they led you throughout all the steps of the analysis, so from data quality monitoring to the very final steps, which are the statistical analysis and the extraction of the results. There are more and more tools available, and they are very useful in the sense you have many Python libraries. Then you have this one analysis framework for CERN that you can run interactive Jupyter notebooks, a huge community from Python that you profit from the statistical methods and the analysis itself. And so all in all, it's an ideal environment to face typical test beam tasks. And yet that's it from my side, so we can maybe move to the...
Yeah, thanks very much, Matteo. So if you stop sharing, I will share the questions, or you could even flip to the tab on your...
Go here.
Okay.
Did they refresh?
Yeah.
So how is it deal with the...
Slightly embarrassed by the fact that it's my question, but people did upvote it. So I was interested in knowing how you adapt to dealing with a data source that's a hexagonal array, which isn't natural for most of the tools in Python data analysis.
When actually what we do is we reconstruct in Cartesian coordinates, and then we map our Cartesian coordinates, mainly the x and y, to the hexagonal coordinates. But then we don't use hexagonal arrays in this sense. For each event, we have
the first step then is to sort of take it into a more Cartesian space, and then you work from there.
In terms of coordinates, yes, but then the bulk of the analysis are the heats and not the coordinates. And so if you have a heat per each position, then you can get rid of this problem.
Okay, super. So I think the second question is actually about visualization for Eduardo. So maybe that's not specific to this talk, and we can deal with it offline. And then the next one is just trying to understand where the data comes from.
Yeah.
Campaign.
These data were with the SKY CMS prototypes of the module, and so they were not already with the HGCAL. So the noise is also different between the effects, because, I mean, between the two chips, because you would have different configurations. And also the bores were not the final bores. They were 6 inches instead of 8 inches. So I mean, the structure of the detector in terms of number of modules and dimension itself was close to the final one, but there are many differences between the detector using the test beam and the final detector.
Oh, yeah.
One of these
I was just trying to understand the specifics of the noise. The wedge in the module kind of gave it away that it was Skyrock too, but I just wanted to be sure.
Yes. Do you believe it can be used in other subdetectors in CMS? Yes, yeah, I think that in principle.
Yeah. Well, one could even generalize that question and say, do you think the techniques that you use here are actually valid for other subdetectors in high energy physics? And could you envisage maybe developing even a package or something like that, common tools?
Yes, exactly. Not only in CMS, but in all the high energy physics subdetectors, right? And I think that the workflow that we followed and that I try to illustrate today is a common workflow in any kind of test beam analysis, or at least in any high energy physics test beam analysis, right? So in principle, you can set up an entire workflow like this and use it in any kind of subdetectors test beam. I think that, for example, Atlas collaboration is using already Jupyter notebooks from some live data quality monitoring in some test beams. So it's some broader CMS or HGCAL only. And yes, to reply to the last question, this is the HGCAL test beam with the Calis AHCAL in the back. I didn't show the AHCAL because, of course, one of the complicancy or the difficulties of this beam test was to make the two detectors, or so the Calis AHCAL and the HGCAL, to work together. And so in the reconstruction phase, you have to synchronize the reconstruction of the two.
Yeah, getting them all synced up must be an interesting operation. And working with such an old detector, especially a prototype old detector, must be a difficult experience as well, or at least lead to interesting flavors of noise, like some of the stuff you were showing.
Yes, exactly. I mean, in fact, really the first part of the analysis itself would be the study of the noise, the pedestrian subtraction, common mode noise reduction, and so all these electronics related studies that you have to perform in order to get to an efficient data reconstruction.